homework you did, yes.
Okay, so I have a solution here of an acid or a base, you think? Acid. Obviously, the pH is below 7, okay, which means that there are a greater number of H pluses, right. In fact, it all comes down to the same photoionization reaction that water loves to do or barely does. Barely does. Now we know that because of its Kw. So let's just write it again. It's all about this reaction in water. Now it's in equilibrium, but boy, I'll tell you, it's more like a completion reaction in reverse. We write it this way. Now I write H plus in hydroxide, but we all know this is the same thing as hydronium as well. So it's not divided by hydronium, it's just it includes that scenario. Now, it barely goes forward because when we do the equilibrium called law of mass action, something we'll define later in the course, we know that this KEQ, because it's for water, we call it KW, is equal to the product of, let's just say, proton and the hydronium times the product of the hydroxide all over the product of the reactants. Don't forget, KEQ is that position that shows no favorability anymore. There's no forward spontaneous process, no reverse spontaneous process. Oh my gosh, I keep talking about it. It's that position, okay, of products and reactants when no more work's being done, okay? And of course, it's essentially products concentration over reactants. Yes, it goes to the respective coefficients, but in this case, as we talked about yesterday, this is a liquid. It doesn't have a molarity, so it's just that. And we know what Kw is. We have measured it with other experiments to be 10 to the negative 14. So the product of these two guys in pure water is tiny. It barely goes forward. Which, if it barely goes forward, then where's the more spontaneous process? By a lot. So really, to write this, I really should write it this way. The proton plus a hydroxide makes water. And this is the basis of neutralization. If you've got a low pH, okay, which makes the a low pH, that is highly corrosive. Why is it corrosive? Because if I've got a great number of protons,
it will go and grab electrons.
It's going to grab electrons everywhere. It's a heat-sinking missile. I keep telling you, that little proton, okay, is smaller than an atom, smaller than a nucleus. So if you look at Coulomb's law, small diameter or distance, tremendous charge. So it's an oxidizing agent. You don't want to have too much of that around. And that's why life doesn't work really well with too many of these guys around. That's why we have to monitor the pH. Now, this guy is also very active for a different reason. We call this caustic. Okay, if you have a high pH, a great number of hydroxides, that's also going to break down things. Okay? And it does it for a little bit different reasoning, but liquid Drano. If you've got hair stopped in backed up in a bathroom sink, you put liquid Drano. It's not acidic, it's actually, okay, a hydroxide. It's sodium hydroxide, it's a lye. And it's very basic, and that strong base will break down the hydroxide. That's with a high pH. So both of these are pretty dangerous. So you can neutralize the danger in these higher lows, or just neutralize extra H pluses with hydroxides, because when these come in contact, they make water, which begs to differ or understand why this goes forward at all. Once this hits one of these, it becomes water, which makes it what? Perfect sense here. It explains why it barely goes forward. Because when these guys hit each other, they reform. So this kind of explains that these guys are really great at doing something. Okay, this guy is really great at doing what?
Tracking.
Well, what does this have? If I do the Lewis dot diagram of hydroxide, oxygen has 6 valence electrons. Okay, hydrogen has 1. Somehow, when this was made, a long, long time ago maybe, it pulled an H from something. This whole thing is -1. Okay, that's called a polyatomic ion. It's a cluster. Okay? Now, H plus has no electrons. So what is it really good at? Jumping on this what? Pair. It's really good at doing that. And what is this really good at? Giving it its pair. That's really the best definition of acid and bases. So if it's really good at doing this, it makes sense we barely make any. And the reason why there's some that exist, what's the concentration? What's the concentration of pure water?
7.
Right? And that would mean if the pH is 7, this is important, if the pH is 7, which means what? This is a what? Negative log of this number. And if you've got pure water, party people, it's got to be 10 to the negative 7. Because we know that this number is 10 to the 14. That doesn't change. So negative log of this is a pH of 7. It'd be a POH. Okay? So it's at equilibrium. But more importantly, the answer is this is so tiny, it has a hard time finding what? This is a small concentration. It's only when these guys collide that they form the water again. So these concentrations are so tiny, they don't find each other. When they do, they make water again, and then this readjusts and makes a new one. What does this look like? Yes?
But how would they break apart in the first place?
They break apart in the first place because there is some stability. There is some stability to be this. Okay? Because it has some stability to be that, these are stable chemical species. Protons, in terms of they can exist this way. Okay? Of course, highly reactive, but they can exist that way. So because of that, there's some pathway in the universe that can break apart. But again, it's so gosh darn what? Improbable, but it does happen a little bit. And because they're in such low quantities, they don't what? Find each other very often. Does that make sense? Okay, good. Now let's do this demonstration. Let's do this. Now, I tried to make a concentration that gave me a pH of 1. I'm off by a little bit. Or my pH probe isn't calibrated. So, what I have here, party people, is I'm having a concentration of an acid, and I'm going to use hydrochloric acid. And there's a reason why we're going to stick with strong acids. Hydrochloric acid looks like this, HCl. It's going to break apart into a proton and a Cl negative. You with me?
Yep.
Cool. Now that H plus is going to make this number get bigger, and the pH gets
smaller.
Right, because it's the exponent, positive value of that exponent. Good. Now I wanted to make a pH of 1. So if I wanted to make a pH of 1, what must be my concentration of H pluses? 1 times 10 to the negative 1. Right. I needed to make a concentration, because to go from here back here, we go 10 to the negative what? X. Remember, this is an exponent. That's negative on a base 10. It's not always going to be a whole number, but these examples, I'm being nice. You with me? What must this be?
Negative.
Good stuff right there. Cool. Now, how do I make a 0.1 molar concentration H pluses? Well, if I'm dealing with a strong acid, hey, it is a strong acid, but we learn strong acids completely dissociate. Their KAQs start approaching infinity or undefined. Meaning, if HCl, and it does, completely dissociate, there's going to be no reactants. You have a 0 underneath. There's probably 1 or 2 that don't. And you're going to have a lot of what? Products. So you're kind of like going toward infinity. Does that make sense? It loves to go forward. In fact, we don't write a double arrow. We show this as a what? Completion reaction. So couldn't you say the molarity of this has to be the molarity of this? Hey, yes. So I made a 0.1 molar solution. Now, HCl is actually a gas dissolved in water. I can't measure HCl as a gas as a gram sample. I have to start with a concentrated form. So I buy this from a chemical supply store. It's 12 molar, concentrated, about 36%. That's the most you can stuff in water. So that's 12 molar. Now, I want to make a 0.1 molar solution because it's going to make me what? A pH of about 1. Again, this is going down.
It was at 0.95, now it's at like...
Yeah, I don't know what's up going on here.
It's getting more acidic.
Well, I know exactly what's happening. I'll explain when we get to the second page. There's something going on. Okay, this is a great little demo, so stay tuned. Okay.
Next time.
Whoa! Help the cliff. All right. Now, so So how do I make 12 molar? Because you need to understand this, party people. I want to make a 0.1 molar solution from a 12 molar. I want 12 molar to become 0.1 molar. So I have to add what to some amount? I have to add what to dilute? Water, right. The moles are going to stay constant. Now I want to make 1 liter. That's what I put in this. I made a liter. So how much of my concentrated acid do I have to add to a container and then fill the water to the 1 liter mark? Party people, MV equals MV. What am I solving for?
V.
How much of the concentrated acid do I need, okay, to add to a container and then fill the water line up to 1 liter? And that's how I solve for it. Dilution problem. Okay? And it was about...
So 0.1 over 12?
Yeah, so 0.1 over 12, which is what? Someone give me that. 0.1 over 12.
Just look on.
0.008. So when I solve for this, I get a volume that's equal to 0.0083. And that's, of course, in liters.
That's not what I wanted.
If you run it to milliliters, then it's...
So I need about 8.3 milliliters, right? Times it by 1,000 to convert to milliliters. I need 8.3 milliliters
That's not what I wanted.
of this.
No.
Then I put it in another container that has a 1 liter mark. I fill the water with that too. Now, really what I should do is always add acid. There's a reason for that we'll talk about. So I should fill some water first, add that little 8.3, then fill back all the way to the liter mark. And I've got 0.1 molar. And that's what I did here. Okay? And the pH was 1. Okay. Now, I want to make some base. I want to make the same concentration of base. I want to make a 0.1 molar base. Now, the base I'm using is sodium hydroxide. NaOH is doing what? Dissociating into Na plus and OH minus. Na plus, this is a salt. It's got a special what? It's got a special polyatomic ion called the hydroxide that affects the swing of pH. Affects this what? Ratio. So it's a base, special salt. Now, party people, I want to make a 0.1 molar solution. Is this soluble?
Yes.
What does it have?
A
Group 1 ion, so because of Coulomb's law, it completely dissociates. To make a 0.1 molar base solution, all I need is a 0.1 molar solution of NaOH, correct? Completely dissociates. And if I use my molarity formula, molarity is equal to moles over liter. I want to make a 1 liter solution. I want to make a 0.1 molar solution. Solve for moles, you get what? I need 0.1 moles of NaOH, which, by the way, is ionic. So I have to measure out grams. Yes?
How would you do the molar of the thing if it wasn't like completely dissociated?
I'd have to use the equilibrium constant to figure out how much it goes forward. That'll be for the spring. We're going to stay away from that. We're going to deal with stoichiometry and direct. So we're going to be doing this stuff without any halfway moments. And then we'll pick that up in the spring. It's a great question. That means you're on it. Love it. Okay? So, NaOH has a molecular mass of 40. I want 0.1 moles of this dissolved in a what? 1 liter of total solution. So 0.1 times 40, I need 4 grams of sodium hydroxide. It's a solid because it's ionic, sticks together to make a crystal lattice. So I need 4 grams, and I basically put that in some water, dissolve it, and then I fill that up to the liter mark, and that's how I made these. And now I have equal concentrations. So theoretically, if I mix those two together, equal amounts, I would have what? Neutral water, correct? Yeah. So in any case, we're starting here. And again, pH is dropping. There's something happening. All right? And we'll speak to that. So now, let's go to this, and let me add some base. Now, as I add base to this concentration, we can consider this for a second. I'm going to add an indicator, phenolphthalein. Now, as I talked about really quickly yesterday, an indicator is a chemical called a chromophore, okay, that will change its conformation, its actual shape, based upon having too much H's and having too much hydroxides. And if it changes its shape, it changes the amount of electrons that can be excited or not excited at all. in this case. We're going to learn about those particulars in the theory part of the course in the middle of the year. But what I'm telling you is these guys have color because they are able to take energy from light and not use all of the wavelengths, and therefore they reflect back. I say that because they actually emit that too, but they reflect back the color they're not using. Right now it's colorless because this phenolphthalein, because of its structure, its electrons are not interconnected, they can't absorb any wavelengths of light. Now, before we continue, I want to go and show you what phenolphthalein looks like. So I want you to understand, it's about structure and function always. So if I look here, and let's go to phenolphthalein. Now, if we go to a table that you see on the reagents, you see phenolphthalein changes color from 8.2. Anything less than 8.2, it's colorless. Anything greater than 8.2, it starts to turn pink, and it's all pink at pH of 10. So it swings. Now, what's going on here? Well, let's go bring up phenolphthalein. Beautiful. There's its structure. Now, to explain what this is, these are carbons in the corner, and they're not showing the H's. This carbon is a double bond to another carbon, and then there's an H attached to it. And that's showing the H's, and they're not showing what the actual carbon. They're showing the carbon backbones, what they do in organic chemistry. So these are carbons. This is a carbon here. This is a carbon. So this is a very big molecule. It's a double bonded to a carbon, single, double. It's called conjugation. We'll learn about this much later in the course. But this is the structure. So H, this is indicator. This is the indicator that has extra H's. And then this is the indicator that loses the what?
H's.
Now, when it loses the H's in the presence of a base, okay, by losing the H's, it changes its conformation. Right now, this dark thing is coming at you. That means this benzene ring we call coming at you. This one is going behind. That's what they're trying to show you that with this two-dimensional image.
Oh.
Okay? This is planar. This is flat. Got one coming at you and one going into the board. When he loses the two H's, because of the protons and the positivity and how electrons work, this readjusts its electrons in a way that this is now planar. This was once what?
Like this.
And now it's flat, and this one, notice,
Turn towards.
this changes, this turns a little bit, this is coming at you. You say, okay, why and how? We'll get to the specifics, but because of this change and connectivity, notice, double, single, we'll learn about this. Because of that change, electrons are more interconnected here. Bottom line is, this is the shape that can use all of its electrons to absorb part of the wavelengths of light, and it reflects back out what it's not using. This is now a shape that can now absorb wavelengths of light. If you put it in an acidic condition, put the H's back on, it changes the shape that it can't. So all these chemical indicators that are in table M, okay, we saw yesterday that I showed you, okay, are all the same thing. They're sensitive to pH changes, and we know what pH they start changing at. So they're indicators of pH by their colors, and you can titrate with that. All right? And there's some other examples. Methyl red goes from red to yellow based upon its changing of shape when it has the protonated form or the basic form. And brimothermal blue changes its shape. Okay? Okay, not a big deal here, so let's get back to reality. Okay, now that you know the basics, I can't just tell you. Let's go back to the demo.
Lager Pro.
Where are we?
Lager Pro.
Yep, thank you. Someone hit.
Oh no.
Bibbidi Bobbidi.
Okay, where am I?
Okay.
No device connected, of course.
Oh yeah. No devices connected. Oh, it's
Well,
1.5.
that's different.
Well, now it's different. I think it lost its calibration. But in any case,
Oh.
Lol.
it doesn't really matter. I tried to make one. It lost its calibration. It looks like it's still chopping a little bit as we go. Now, if I add some base, what do you expect to happen?
Depending on the pH.
Well, we're going to look at two things. The pH is going to what?
Increase.
Right, because I'm increasing the hydroxide concentration. But remember this. We have a lot of H pluses beyond what the water's producing. Right? So the extra H pluses are going to hit the hydroxides. And we're going to make water. So I'm going to take away the extra H pluses. That's the first thing, right? The first amount of NaOH I add is going to neutralize those extra H pluses, and the pH is going to go up. It's going to take some time to go up because there's a lot of H pluses. What's really cool about this is as I pour this in here, you're going to see the fuchsia pink color start appearing. It appears because in that part of the solution, there's more hydroxides to take away the H's off of phenolphthalein to make it absorb color. But as it moves to the other part where there's still too much H pluses, it's going to change back into the colorless form really quickly. As I get closer and closer to 7, this color is going to persist more because there's less H pluses to neutralize. Does that make sense? It's really, really cool. And again, love it. So let's do it. Now, it's a rough titration because I should be adding a very constant stream, but I'm just going to kind of pour, okay, the best that I can. Now,
Oh yeah, you can slightly turn it pink and it goes away.
there's not much going on because there's so many more H pluses, right?
Yeah.
So you do see a little bit of color, right? But that color is going to start persisting. Why is it disappearing?
It's moving into the areas with a lot more.
What's moving?
The
iron.
And I should be. The phenolphthalein gives me an indication of what? Where the hydroxides are. Hydroxides are in high concentration, but once they hit the H pluses that are higher in concentration, it's making water. So I added all this base, yet my pH barely changed. Why? So many H pluses were eating up the hydroxides. Now, once I start running out, this should be climbing faster. And you should see the color persisting more.
It's already persisting a lot.
Notice,
Whoa.
it's almost there. Clearly, I didn't have to add that much in that part. Okay? It's still climbing up. Why? Because I ate away most of the H pluses there, and now it just needed a little bit more. It's an exponential change. Okay? I've been to pool stores trying to figure out a gasket that I needed to fix something, and I watched it. So I was there for like over an hour trying to figure out what gasket, and it was in a catalog because I had some old piece of equipment. Okay? I always fix my own stuff. And a guy came in 3 separate times. He had a chemical to raise his pH, lower his pH, and raise his pH. He noticed it took 5 pounds to get his pH to a certain value. He thought if it takes 5 more pounds to lower it the same amount. So he went under, so he had to get pH up. So he had muriatic acid to drop the pH of his pool. He dropped it too low. He had to buy some base to go up. Guess what? He ate it too much. He was there for 3. I wanted to step in and say something, okay? Because he was not getting any help and he was buying a lot of chemicals. So I have an HCl.
This man is fun.
Okay? So I'm going to go the other way now. That's it.
Hey, it's a
Stop. I hit collect. And we're going to start high now, right?
Yes.
Yeah.
Okay, now, I'm in a basic range. You're going to add acid. Same thing's going to happen. But now you're going to see it go clear and not persist, right?
Oh, okay. Whoa.
Well, I'll tell you,
That's a cliff.
that was a cliff. I felt like, so this must not be 0.1, this must be much stronger. I
Yeah.
added a lot less, didn't I?
Uh-oh.
Okay, not sure what I grabbed there. Okay, notice there's an exponential change right there. That's a perfect, what we call titration curve. You know where's the middle of this? Where's the middle part?
I guess.
Yeah.
There, yeah.
Yeah.
That's where we find neutralization. The closer you get to neutralization, the more exponential it goes up. Couple of drops past it. Of course, we want to go back because it's fun. Okay, so let's go with some base. Okay,
It's got like skyrocket.
We did this with Miss Latito and we used like the literal dropper.
Ooh. Oh. Ah,
okay.
UA's for UA.
All right, you get the idea.
Keep
Okay.
going.
Pour all of it in. Let's just go really high.
Well, I'll only get as high. It only starts approaching the concentration I made.
Yeah.
Okay, so party people, let's get rid of that. So let's go to the first page
We
of
need
your
value.
packet. Let's continue on.
All
All right. All right, we are. All right, so here comes some definitions. and has everything to do with what we just saw. I'm gonna move this back without probably crashing anything. Okay. All right, party people. So we got to define these. So let's do that. The easiest and the simplest, most definition was the first one that came out, and it's by Savant Arrhenius. Okay, he had the first definition of an acid. Now, because it was the first, there was a lot of acids he didn't know about. His definition was not the most, it wasn't the best. It wasn't the most all-encompassing definition. He left out some acid and bases, but it is the first definition, and this one is on your regents. Okay, and to be an Arrhenius acid, ooh, little mark there. All he said, party people, was to be an acid, all you had to do was deliver H pluses in solution. All this means is that that acid was responsible for making protons into the solution. It's very simple. And it's not the best definition because there are some acids that actually don't have any H's in it, if they're acids. Okay? To be a base. Now, table K, for those new to this, is a table they give you in regents. And notice something, if it's an acid, they scream and tell you it's an acid, putting the H in front. That's the what comes off. So all of these guys right here that I'm putting a line under are Arrhenius acids because they deliver H pluses. Think about it. If you deliver H pluses in solution, you must have an H plus that comes off. That's essentially what an Arrhenius acid is. What do you think an Arrhenius base is? You deliver OH, right? So in solution. OH minus in solution. Okay? And if you notice, table L is given to you, and these three bases are Arrhenius bases because they have hydroxides. Notice they're just three salts. These are hydroxides that come off from a salt because they're soluble. Okay? This one is not an Arrhenius base. It has no hydroxides. Yet we know when we drop ammonia in water, the pH rises. Okay? So this is not the best definition. So let's deal with NH3. And by the way, NH3 comes under the Bronston-Lowry definition, which was a newer definition, a more recent definition that encompassed chemicals that didn't fall under the very easiest definition. And ammonia is one of them. So here's an example right here. Let's look at this right here. We have ammonia and water. Now, I'm going to tell you what it does. Ammonia has a lone pair. Nitrogens are very famous, have a lone pair. This lone pair in nitrogen gives them basic qualities. In fact, organic bases in our body have lone pairs on the nitrogen. In fact, nitrogenous bases are nitrogens, okay, that are part of the bases in our DNA. In any case, here's what it does. This lone pair really attracts an H from the water. So it's able to accept this proton. And you can understand why that happens. Think about this. I'm oxygen. I've got two H's. I'm tugging on the H's electrons closer to me, so H is kind of dangling out there as a proton. That's why it's polar, it's positive. Well, hey, nitrogen's got a lone pair sitting out there. So an H plus who kind of had its what? Electrons pulled away will love this lone pair. And so that ammonia takes an H plus from the water. You know what it makes? It makes, yeah, but it makes NH4 plus called the ammonium ion. And right, absolutely, it makes the hydroxide. So it doesn't deliver the hydroxide, like Arrhenius said, based upon having the OH and it sloughing off. It actually delivers the OH by accepting an H plus or a proton. So the Bronston-Lowry definition is not about delivering a proton or hydroxide. It's about donating or accepting protons. So to be a Bronston-Lowry base, you are a proton acceptor. Just accept it. And to be an acid, guess who the acid was here? Yes, water was acting as an acid. It was a proton donator.
Is that why the pH was going down?
Not yet. We're going to get there. That's the next definition. Now, party people, we have very famously under this definition something called weak acid-base equilibrium. Okay? And so I know that ammonia is a base. Now if I didn't know that, I was given this entire reaction. Watch. Here is the current condition. This is the future. In the future, ammonia becomes ammonium. Hey, in the future it has one more H. How'd that happen? It must have accepted, so that's your base. This guy's an acid, how do I know? In the future, it has one less. So it must have given off that H plus and acted as an acid. In the reverse, crisscross, everyone, I'm sorry. In reverse, OH minus is becoming what? H2O. So how'd that happen? It must have been accepting an H plus, so we already know that what? The reason why the hydroxide is a base in the Bronson library definition is because it accepts protons. And to make what? To make water in the reverse. So I'm going to draw a double arrow here. It should show a double arrow because this is equilibrium. So this is acting as a what by accepting a proton?
Base.
Molarity base. This guy in the future, to go back to reality, had to donate and lose. This is an acid. Now, notice we have acid and bases on both sides. This would be equilibrium. Why? We don't have strong acids or strong bases here. If I did, one way. Weak acid and weak bases will do this. Now, new word, party people, conjugate. Conjugate means same chemical plus or minus 1H. So, who's the same chemical here? NH3 and? No. These guys differ by one proton. That's a conjugate acid-base pair. Stay with me. Conjugate acid, I'm good at doing what? Donating. And my conjugate base is good at accepting. So if I have the base and I want the conjugate acid of the base, well, if I have the base, what do bases do?
Accept.
Should. So the conjugate acid is going to have one more proton than my conjugate base. So if I have a base and I want the conjugate acid from it, I add 1H. So I lose 1H, right? I want the acid form. So this is my base, okay? I'm sorry, this is the conjugate acid, sorry. This is my conjugate acid, and I want the what? Its base, okay, to be the conjugate base of this form. What happens after it donates a proton? It has one less. So the conjugate base is always one less proton of the conjugate acid. Here I have the conjugate acid. Its conjugate what? Base has one less, but they're the same chemical. So let's identify them. Conjugate acid, conjugate base, that's one pair. And here's another pair. Conjugate acid, conjugate base. They're the same chemicals, plus or minus 1. All right? H. It's the result of acting as an acid. I have one less H.
Will the following students please come down to the main office? Adam Sharon.
Take a break, please.
Zoila